welcome to the lecture number 37 of the machine learning course. And in this particular session, we are going to talk about the convolutional neural networks. So let us try to understand the requirement and some background about the CNNs. So I'm just going to give you a simple example related to the same thing we have done earlier also. That let's assume that you have a noisy sensor. What do I mean by noisy sensor? That let's assume that the reading is 50, it gives you some noise is a fundamental property of any system, and noise would always be there into the system. So instead of 50, sometime you get 48, sometime 51, and sometime 53. So there are some small variation into the actual value that actually you get. So there is a noise. Let's assume that there is a noisy sensor that you have, and you want to find out, you want to estimate that what is the actual value at the particular time. So various values are, let's assume that they are given to you, and if at a particular moment of time you want to understand that what the actual value, because you cannot directly rely on the sensor data, because you are aware that there is some kind of noise is there. So what would you do? So the direct answer would be that sometime if you are not sure about this value, you can take the average. So maybe you can take for this particular duration all the values you take and find out the average, and you assume that this value is going to come at this particular place. Um, this is the right strategy. Sometime many other time you see that you, because you know that you sometime you assume that the noise have a zero mean distribution, and therefore if you find out this kind of summation, the average the value that you are going to get is actually not far from the actual mean of the system. So this is the right strategy. This is going to be the right strategy. But however, you may also think that values that has been to the very near to the thing. For example, if you want to estimate that what is the value over here, so the response means the importance of this value is more as compared to this value. So sometimes you may also think that why to put all the items at the same weight? Why cannot I vary the weight, and the items who are far apart, they may have been given less importance, near items are given more importance. So we can do something like that. And this kind of thing is called the weighted average, and we can provide the weights and we can multiply. For example, here is a small example for you. Let's assume that this is the value that is coming from the sensors. So what is the coming from the sensor? So let's assume 1, 1.0, 1.2, 1.4, 1.71. These values are coming to you. And now you want to understand that what is the actual value. So actual value at this particular point, if you want to find out. So let's assume that you come up with this kind of weighting scheme, where the current item is given the weight 0.5, previous one is 0.4, then 0.04, 0.02, 0.02, 0.1, 0.01, and then you multiply these values and find out what is the summation, and find out what is the summation, and then you get what is the value over here. Interesting idea. Okay, so this is logical to do. So the same kind of things, same kind of operations we are going to do for the images also. So we have seen into the previous sessions that sometime it may be possible that if you want to find out the actual better representation of this image, so better representation. So if you want to find out what is the pixel, what should be the value at this particular location, so you see the neighborhood into the original image. You go to the original image, see the neighborhood, and you find out what is the average over there. You replace this pixel with the average value. We have seen that this kind of operation is going to give you some blurring effect, and it has a smoothing effect, as we have seen earlier, that very far apart values are actually going to replace with to the neighborhood values. Here is an example that since the things are into the two-dimensional space, so let's assume that this is the image that I have, and let's assume that this is the kernel. Kernel has 4 values. It is a 2x2 kernel where we have 4 values. So if you want to find out the value over here, you put this kernel at this particular place. You put this particular kernel at this particular place. What do I mean by this? That you know that w, x, y, z. So w, x, and y and z, these are the values. So what should be the value at this particular location? It is a multiplied by w plus b multiplied by x plus e multiplied by y plus z multiplied by f. So this is the value that is going to come over here. What should be the next value? What is the value at the adjacent place? So again, you can apply the same thing. You put the kernel over here. You see that W multiplied by B and C multiplied by X and F multiplied by A and G multiplied by Z. Then you can put it here, but after three places you cannot put. So the original image was 4 class 4, but actually you get the output that is 2 cross 3. Why? Because I think it was not 4 cross 4, 3 cross 4. So it is 2 cross 3. Because when you put into this particular line, after that you cannot slide this particular kernel. So you are going to get something of different size, but this is what the output you are going to achieve. Any problem in this? Hope this is clear to you, that if you want to find out the things, you have to modify, take this slide small kernel to complete the image, to the complete image, and you would be getting something different. As an example, we have seen that if this is the image and you multiply with this kernel, that is 111111, and we assume that there is also 1 by 9 is written over here. So what is the thing that you are going to get? You are going to get a blurred image. Similarly, let me tell you that if you put this value, that is -1, -1, -1, -1, and 5, means what? That you are going to put more weight to the what is you are going to seeing at the current place, and you are subtracting the nearby information. This is just like that you are going to remove some of the high frequency components. And actually, what does it mean? That you know that into the last class we have discussed that the low frequency component actually contains details. So actually you are increasing the detail into the image. So what would happen? You would be getting this image, and if you compare, I don't know that how visually it is more clear, but if you try to see that here the clarity is more. Okay, so it actually, this particular thing actually sharpens the image. So the image has the higher sharpness. Similarly, this kind of thing where 1111111 minus 8, this value detects the edges. So from this particular slide, what I wanted to tell you, that different kind of filters are going to have different kind of effort on the image. Some of them do blurring, some of them do the sharpening, some of them do edge detection, and different kind of operations uh, can be performed using by applying these kind of uh, filters. So we can say that this filter is going to give me some kind of, this filter is going to give me some kind of this filter is going to give me some kind of features of the image. Make sense? Generally the images are the 3 dimension, and you know that okay, generally images are of the 3 dimension, and if the 3 dimension things are there, so instead of one value, one set of values you have actually 3 set of values. So if you want to apply a filter, then you can apply the filter on the first phase, the second plane, and third plane. RGB, three planes you have. So that would actually not be a right idea to apply, because if on a single pixel, if you want to find out that what is the representation of that thing, so you should go into depth also. So this brings us the very important idea that this filter should not be only 2 dimensional. It can also be a 3 dimensional filter. What is the third dimension? What is the third dimension? If the filter is of the 3 dimension, what is the third dimension? So you know that this third dimension is actually going to be the number of planes into the image. So if the plane has 3 dimension, the input should also have the 3 things. If the filter is, for example, 5 cross 5, so 5 cross 5 filter you have, and you want to apply this onto the RGB image, then how many 5 cross 5 values you need to have? You need to have 5 cross 5 values over there. So overall, how many values? 3 multiplied by 5 cross 5. These many values of parameters are needed. Okay, so if you understand this particular part, so you can also think into the same way that instead of applying one filter, because you know that if the values are all values are 1, then it means something. So few values are 1, few values are 0, then it means something else. So why not find out different features? So if you want to build the multiple features, You can apply multiple such filters. So if you apply multiple such filters, for every filter you are going to get a plane. So at the output side, you would be getting multiple planes also. Make sense? So what I wanted to tell you, that filters are the three-dimensional. Number one thing, the filters are of the three dimension, and the multiple these dimensions are actually going to tell that what is the depth of the image. Number one thing. Then we have talked about that multiple filters can be applied. Having the depth, the multiple filters can be applied. Meaning what? That they are going to build different feature maps for the image. It is a very interesting slide that actually I wanted to tell you that. Okay. So till now we have understood that what is the filter. What is the filter? Filter can be two-dimensional filter. So one thing that I wanted to tell you over here, that let's assume that you have an image of say uh, A cross B. Means there are what do I mean by this? I mean by this that there are A number of lines into this direction, and B number of lines into B number of pixels into the in B number of rows and A number of columns if you have. And if you have a filter that is say F cross F, okay, if you have a filter of F cross F, so you may assume that if you put the filter over here, okay, you'll be getting one value out of that. Then you can shift this filter, you can put the filter over here one place before, you will be getting one value by this. Then you can again shift it here, you will again be getting one value. So how many values you are going to get into this particular direction? Can you tell me? If there are a number of rows, so a minus f, because a, if you are going to, if what I wanted to tell, that let's concentrate on only one direction. Okay, just concentrate this particular direction. How many pixels are there? A pixels are there. My filter size is f, I can put it here. So how many values are here? A minus f values are there. A minus f values are there. Okay, if I say that my filter is placed at this particular location, then how many values are here? Because here how many values are there? F values. Filter size is f. How many values are here? A minus f values are here. So all of these are going to give me one value. When I'm going to put the filter over here, they are going to give me one value. And one value would be given by the filter when I'm going to put the filter over here. So total number of value that I'm going to get is A minus f plus f, 1. A minus f plus 1 number of values I'm going to get into this particular direction. What is happening into this particular B direction? It is B minus f plus 1. So very interestingly, that I wanted to tell you. Are you able to understand this? That if an image, if a array of A cross B is there, and if I apply a f cross f filter on that, then the output that I am going to get, it is A minus f plus 1 times B minus f plus 1. This is what the size is going to be. So this is how the size changes with respect to the filter. All right. Sometime, so let me just quickly write this thing. So what I just told you, I told you that if there is A cross B image and you apply with the filter F cross F, then you get the image that is A minus F plus 1 times A minus F plus 1. This is what the size you are going to get. The output is going to be of this particular size. So this size is going to reduce. Sometime what you want, that size should not reduce, so you can put some more pixels over here so that this size becomes correct. So let's assume that you are going to put the p number of pixels into one side. So p is a padding. If I say that I'm going to do a padding, means I am going to put p number of pixel into this side, p number of pixel on this side, p number of pixel over this side, then my image would, the size of my image that I'm going to consider is going to increase, and then this size is not going to be this. Instead, I would be getting a bigger image. What would be that size? So it's not very difficult to see, because now the image is that you are going to consider is not a by b, it is a plus 2p, because both the side p is there, multiplied by b plus 2p. This is what the size on which you are going to apply the filter. So what is the output? Here the same formula, a plus 2p minus f plus 1, because the size a becomes a plus 2p. This is a simple formula. A plus 2p, I think it should be b plus 2p minus f plus 1. This is this size image you are going to get. Make sense? Very simple. Very interesting idea. So this is how you get, this is how you apply the padding, so that the size, now you can see that this size is going to be the larger, this size is going to be the larger, so therefore you are able to, you can accommodate more things onto the system. Okay. Next important concept is called the stride, and actually stride means what? Okay, 1 minute. Stride means what? That when you are going to go into a particular direction, for example, let's assume these are the pixels over here. Okay. So when you put your filter over here, you are going to get a value, because you get a value over here. But if the stride is s, let's assume that stride is something that is having a value. So you are going to consider s things over here. And for these s thing, at this particular location, you are going to get a value. If the stride is 1, so if the stride is 1, so when after this item you are going to put the filter at this location, at the filter this location. But if the stride is 2, then from after taking the value from here, you are going to put the filter at this particular location. And similarly, you are going to leave one place and you are going to put things over here. So this is the importance of the stride. Okay, you are going to leave one items in between. So after this thing, you are going to again consider s number of item, and you are going to take the what is the value over here. Okay, you know that that this is if the length of this particular sequence is L, so you are going to L minus f plus 1 values. If you apply a filter, then you are going to get the L minus f plus 1 values. But if you apply the strides, then how many values you are going to get? So I'm not sure about this. Let's assume that t number of stride, this is the first stride, this is the second stride, dot dot. Let's assume that the last item has been produced by the tth stride. So how many items over there? It is s multiplied by t plus 1. These many number of items are there into this thing. And this value is going to be L minus f plus 1. Okay. So you can say that t is equal to, what is the value of t? T is equal to L minus f divided by s. How many values you are going to obtain into this particular setting? T after every stride you are going to get a one value. So t value you would be getting, and one value was you got at the first place. So total number of values that you are going to get is L minus f divided by s plus 1. Make sense? We are thinking that the padding is not there. If you apply the padding, you can add this to the formula also. So the overall formula, if you are actually applying the padding, if you are applying the stride and filter everything, if you want to find out the overall formula, so if what is the value of new height and width when let's assume that this image has the height and width, then what would be the next size? It is going to be that h minus f. You can see that instead of L, here we have h. I'm going to talk about that. Instead of L, if it is h, If these many number of h number of items are there, so your formula is going to be using the same thing. You can think that L minus F divided by S. Okay, this L becomes L plus 2H 2P if there is a padding. Similarly, this W becomes W plus 2P if there is a padding. You divide it by S and add 1 over this using this particular formula only. Here there is a small typo. This S should be W. Okay, if you want to find out the width, if the height and width are there, so you can see that what is the next thing. Okay. So, so a small exercise for you, that this is the scenario that we have. Can you tell me that? I hope you understand this formulation. It is very easy for you. I believe that for you people, these formulas are very easy. So let us solve an example where you have an image of the 227 cross 227 and 3 channels are there. You are going to apply a filter that is of 11 cross 3. First question, can I apply a filter of 10 cross 10 cross 3? Yes. Can I apply a filter of 10 cross 10 cross 4? Answer is no. Why? Because this 4 should be here also. If the number of channels into the image is not 4, we cannot apply 4 over here. So this 3 should match with this particular 3. So this is the one thing, that because otherwise, because it is going to be into the depth now. So if this filter is going to be applied on this particular image, what is the size that I'm going to get over here? You can apply this particular formula. Assume the stride to be 4. What is this? Let's assume that we are going to apply 96 filter. So if you are going to apply 96 filter, so how many values I am going to get? How many planes I am going to get? 96. So first thing is solved. What is into this particular direction? You say you can apply this particular thing. What is the padding? Padding is 0. So in this particular formula, 227 minus filter is 11 plus 0 divided by what is the stride is 4 plus 1. So this is the size. Can you find out that what is this value? It is going to be here, and the same value is you are going to get over here also. So this is the output. So input was this. You apply this particular filter. What is the output you achieved? This is a very interesting thing. So what ultimately with this image I got this feature. What you should understand that for this image you got this particular feature. That's it. This was the image. Sometime you want to apply a kind of classification. For example, this image is there. You want to classify whether it is a car, it is a bus, or monument, or flower. So you can use this to say something. For example, this is the image, and you want to say what is the classification of this particular item. Once again, our task is to into the machine learning is to do some kind of classification, some kind of thing. So let's assume that this is the image that you have, and if what you want to do the classification, how would you proceed? Whether you would use the raw pixel? The answer is no. Why? Because raw pixel, if I add 20 to all pixels, the image would remain the same. However, the pixel values have changed. So working on the raw pixel is not a good idea. Instead, you should find out some feature, such as you apply a edge detector over there. So you are going to get the new image, and on this image you apply some learning thing, and this classifier, and that classifier can tell you that what kind of item over there. Sometimes you may think that we can apply the more sophisticated ideas, such as scale invariant feature transform or histogram of gradient, and these things you can apply. You get those kind of features, and then you can combine, and then you apply the classifier on the maybe some learning classifier over here that can tell you that what is over here, and then you can do the classification. Once again, from this slide I wanted to tell you, given the image, you want to apply some kind of method to find out the features. When you get this feature, then on these features you apply some kind of learning mechanism to do the classification. Is it clear? The question is this, that where the learning is happening, where the learning is happening, whether the learning is happening here or here, Answer is the learning is happening here. It is not happening here because I have done these things by handcrafted method. I have find out some features. So I'm not learning here. I'm only learning here because I have to change the parameter so that my accuracy is higher. So is it possible? The idea is this: is it possible to learn these kind of features also? And very important thing comes that when you start thinking into the direction that is when I was learning, I'm only learning at this particular place. Is it possible to learn at this particular place also? Can I do something like this? So here comes the convolution. Here comes the CNNs. The importance of the CNNs. So this was the image. I can pick various features out of this if I apply various kind of filters out of this. And sometimes you can also think, because you know that applying a particular kind of filter is going to give you different kind of feature. So you may also think that after having this thing, you can again apply some kind of convolutions over here. Then you get the higher level of the features. So now you can build the feature hierarchy by using the convolution operation. Original image, applying the filters, getting the feature. On the feature, applying convolution to get the more complex, more involved features out of that, hierarchical feature out that. However, we know that if a complete image is there and you are going to put a filter over there, the filter is going to work into this particular area only. Filter is going to work into the small area only. Is it a right thing to go ahead with, because it is not representing the complete image? It is going to see the small area only. Looks like that it is that if it would be better that if this particular thing is connected to all the things, because then more information would be there. But essentially what happens that if you try to visualize this onto the very higher level perspective, then you can think that if multiple layers are there, then at this particular layer they are connected like this, and next layer they are connected to the more things. And when you go to the deep down, you would be actually seeing that all the pixels, this particular thing, this particular value is going to have all the interaction with the all the pixels which are there into the image. So by building the hierarchy, you can get the the features which interaction which are there into the bottom. However, you can see that this is only having the interaction, direct interaction of these values, but indirectly it also have the what are the things over in this particular level also. So by this you are going to get the combination of the thing at this particular place. Okay. Importance of the CNNs is this, that they are filter based, and therefore having the filter, the very important thing is this, that the same weight which are you are going to apply, they are going to apply onto the complete image. That is important actually. Why it is important? That is why it is important. So you know that, let's assume that you have an image and you are going to apply a filter over here, and you are going to apply a filter here also. My question is, should you use the same value here and same value here? Sometimes you may think that it would be better that if you use a different value here, different value here. Sometimes you may think in that particular direction. But this is not important. This is not a right strategy. I tell you why. The reason is this, that sometime, because you know that the fix this particular fixed pixel is going to get a feature. And let's assume that it is getting the edge feature. Okay, where are the edges? So if in an image I'm going to highlight that here where are the edges in this particular region, then should I ask here something else? The answer is no. On the complete image you are going to apply the same operation. So having different filters means what? That you are going to apply different operations on the different area. That is not good, because if one time if you want to find out the feature, then on the feature, into the complete image you should find out that feature only. You should not go to the different features. Make sense? So weight sharing is very important, and it is a sensible operation, because on the image you want to apply the same kind of operation throughout the image. uh, then also there comes a very interesting idea that is called the pooling. And pooling is what? That for example, if this is the input and you apply some kind of filter and you are going to get this value, pooling actually directly gives you a handle to reduce this size. Why to reduce this size? Because you are getting sometimes you want to get the important things and you want to reduce the computations. So it gives you a direct handle that how can you reduce the size. So pooling can be maximum, minimum, or average, and it is again a kind of, you assume that it is a filter, but however it is not a filter. Let's assume that you are applying a 2x2 filter with a stride of 2, and you are applying a max pool. So pooling can be maximum, minimum, or average. I'm going to talk about that. So 2x2 means what? First you are going to get over here, and in this particular thing, you, if it is a max pool, you find out what is the maximum value. You know the maximum value is that, so you get it. Stride is 2, so next filter you are not going to put at this particular location. 1 2, you are going to put the filter over here. What is the maximum into this particular area? 4, so the value 4 is here. Again into the next line, you would come back into this particular place, go down. So 1 2, because stride is 2, so next item would be computed from here. 7 6 9, so highest is 7, so you got 7 over here. Next thing, 4 5 1 2, you know highest is 5, you get 5 value 5 over here. So this is what the new thing that you are going to get. If the stride is 1, then from this particular location, next item would be considered from this particular location. Again, you would be getting 8 over here. Then third item would be here. Similar operation you can apply, and you can find out that what is the values over here. So can you help me to find out that what is the value into this particular place? You know that this place would be computed by this, and you know that the value maximum into this particular 5 is 5, area is 5, so value is going to be 5. Am I right? Okay. How to train? Let's assume that when all the things are, you put various layers, then how to train? Again, the same idea that we have earlier, that you can apply the back propagation. With this, we come up to very important historical neural network architecture that was using the CNN way back around 1998. This was a paper from Yashio Bengio. He's a pioneer in this particular field, in ML field. So he have developed a method called LeanIt5, and it was like that. It was for the character recognition. So let's assume that are given. Digits are given. So digits could be 1 0 1 2 3 4 5 6 7 8 9. So 10 digits could be there, and then this system is going to tell you that what digit is given into this particular input. So what is the architecture? Architecture says that you are going to apply on this particular image filter size of 5 cross 5. How 5 cross size 5 filters you are going to apply. Okay. How many such filters are there? 6. How many such filters are there? 6 such filters. So one filter has the 5 cross 5, so 25 values. How many filters? 6 such filters. So these many number of parameters are needed. So 150 parameters would be there. So stride is 1. So for all the items you are going to get, it is 32 cross 32. So stride is 1. So it is 32 minus 5 plus 1. This is the size that you are going to get. What is this value? It is 28 cross 28. So you can see that the output is going to be 28 cross 28. 6 output would be there, because every filter is going to give you one output. 1 2 3 4 5 6. So this is what the output is going, you are going to get. Into the next layer, it says that it is a pooling layer. So max pooling is done. Filter size is 2 by 2. So into the 2 by 2, you are going to get a value. So 28 becomes 14 by 14, because into the 2 by 2 area, you are going to get one value. So therefore, it is going to be 14. K is equal to 6. Again, 6 filters are there. 1, 2, 3, 4, 5, 6, because everything is going to give you one. And how many parameters? 0 parameters, 0 trainable parameter, because you know that what to be done into the pooling. You need not to have any trainable parameters. So 0 number of parameters are there. Then comes the next layer that have filter size again 5 cross 5. So, but this time this 5 thing would be need to be multiplied by this complete deck, because there is a 6 there are 6 things over there. So they need to be multiplied by 6 things over here. So this is the size of filter. And how many such filters are there? 16 filters. So multiplied by 16. These many number of trainable parameter. Find out this value. You can put it here. What is the training parameter over there? You can find out there. If I ask you that what is the output size of this particular layer, so you can again apply the same formula. It is, since it is a 14 cross 14, so 14 minus f is equal to 5, because filter size is 5 plus 1. So you can see that this is 10 cross 10. So 10 cross 10. How many such? 16. 1, 2, 3, 4, 5, 6, 7, 8, 16. 16 such things are there. Find out that how many parameters are there. Then after that, again, there is a pooling layer. It is again 2 cross 2. So 10 cross 10 becomes 5 cross 5. 16 such things are there. The 16 values are there. Okay. So how many values are there? When you get the output, you see that in every layer there are 5 cross 5 items into 16. These many numbers of items. You add one on that because of bias, and next layer is the fully connected layer. So every pixel over here is connected with every pixel into this particular thing. How many values are there? 120. So multiplied by 120. These many parameters are there into, because these many trainable parameters are there into this particular layer. Next layer, since 120 items are there, 120 plus 1 multiplied by 84, 84, next layer has 84 number of neurons. So these many number of neurons are there. Next, final layer has a 10 neurons. Why? Because 10 number of classes we have. So this is how we create the architecture. This was a wonderful architecture. However, because not much processing power was available, so this was actually a kind of discarded at this particular time. A lot of handcrafted method people tried developing, but after development of a lot of libraries and a lot of availability of the GPU power, something very strange happened around 2012. The story is this: there was a Imagenet challenge. This ILSVRC, that is the Imagenet Large Scale Visual Recognition Challenge. And into the Imagenet, there are Imagenet was a database collected in 2009 with 22 categories. 22K categories means 22K categories means 22,000 categories. How many categories means what? For example, banana, bus, car, truck, bird, scooters. These things are leopard. These things are categories, and there were 14 million images. But for the purpose of this challenge, they have actually extracted some images from that 14, 3, 1, 1, 6, 7 number of images, and that images can had only the 1,000 number of classes, and they have run a experiment challenge that find out that the highest accuracy possible. Very interesting that somebody came, some method came that with the accuracy of that has an error rate of 28%. And it was a handcrafted method that was using HOG, LBP, SVM, etc. Next year, people has improved it into the 2011. This error was reduced to 26%. But suddenly, it's 2012 when LXNet actually was introduced. By getting the inspiration of this LeanNet, they have suddenly reduced the error from 26% to 16%. It was a phenomenal decay into the error rate, and that's why the people started thinking that can we improve further. Next year, the same architecture was optimized, and people have shown that if it have optimized well, instead of 16, the error rate should have been 12%. So the same architecture, so with small modifications, and they were able to achieve the 12% of error rate only. Huge improvement. So when this would come to your mind, that when you have a model, you want to optimize it. After optimization, you think that how can we add more power to this. So earlier it was a 8-layer thing, then the VGG 16 and 19 came, and it tells that there are 19 layers. With the 19 layer, it has reduced to the 7.3%. Then people further improved it by telling that why not to see the things at the different scales. So it further improved. Error was further improved to the 6.7%. You know that the human have the 5% error on this particular data. Next year, the bigger model that is called the ResNet came, and that has it reduced the error from 6.7 to 3.6%. 152 number of layers, gigantic network that has the very large number of layers, very difficult to train, but they have somehow managed to train it, and the error reduced to 3.6% only. Wonderful network. But after that, there are some ensembles and SENet, but those things are not much important, because when you are getting better than the human accuracy, people think that we have achieved our goal of the artificial intelligence, and maybe the system is actually overfitting, and we should not go beyond these particular boundaries. Let us one by one see that what is the architecture of these things. So we would see the first architecture of the LXNet. So as I told you that LXNet is a 8-layer architecture. So there are 8 layers. So input image, the input image is of 3-channel input image that has a size 227 cross 227 ImageNet images, and then it applies 96 convolution of 11 cross 11. So first thing was 96 filters of the 11 cross 11 with the stride is equal to 4 has been applied. So you got this thing. Then after that, it applies max pooling with filter size 3 cross 3 and S is equal to 2. So you got um, max pooling. Then again there is a convolution, then max pooling, then convolution, then convolution, then convolution, then max pooling. After that, 3 layers of fully connected thing having 4096, 4096, and 1000. Why 1000? Because you know that in this particular database, how many categories were there? ImageNet challenge, 1000 categories were there, na? 1000 categories were there. So at the last layer, there is a 1000 category. So this was a wonderful paper that appeared in NIPS 2012, and a lot of citation it has gathered. So this was the architecture. As I told you, ZFNet came next year. That was just a simple improvement on the previous thing. So what was the improvement? Improvement was this, that first improvement was this, that LXNet was using 11 class 11 over here. They told that I'm going to use 7 class 7. And many other things were same, but here then again there was a difference, that instead of 384 they put 400 512. Instead of 384 they put 1024. Instead of 256 they put 512. So everything is going to be increased over at this particular place. However, this output is going to be the same, 256 cross 256. This output they have make same. So the same architecture with the some small more power was able to perform the better. And as you have seen a few minutes back, that instead of 16% error, it has 12% of error. Am I right? Yeah, 16 to 12% error. So next idea was that why not increase the number of layers? So VG16 came that has 16 layers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have the 16 layers that it has. So max pool, we don't count it as a layer. Why? Because they don't have a trainable parameter. So who are we only count the trainable layers. One more simplification that VGG has done, it says that I'm going to everywhere use the same kernel size, that is of the 3 cross 3. So lot of parameters, and it has also, as we have seen, that it has also achieved a very excellent kind of accuracies. Next idea is very interesting. It actually says that why you are seeing the thing into the same layer, Inception net or the Google net. It says that why you are going to see the things on the same level, same zoom. You see the things on the different zooms. So it says that apply different filters. Some filters have the different size. So it says that instead of using one filter, I'm going to have multiple filters. So 1, 2, 3, 4 multiple filters is being applied, and then the output has been put one by one behind other. So by this you are going to get a big feature vector that is going to be a good thing. However, if you put more filters, so number of parameters increases and the computation also increases. So you have to do more computation. To simplify the computation, they have also introduced one very smart, interesting concept that is called the one by one convolution. Okay, one by one convolution. So what do I mean by one convolution? So one by one convolution is this. For example, let's assume that you have in this image that is W cross H, and it is has the depth D. So it says that if I apply a filter, I would be getting a value over here. Okay, let's assume that D is 1000. So if I apply a filter over here, I would be getting one thing over here. Instead of 1000, if I apply, for example, 20 such filters, so I would be getting a smaller plane. So instead of using this thing to do a computation, I'm going to utilize this thing for this smaller one for doing the computation, where D1 is very less as compared to the D2. As I told you, if the D is 1000, D1 could be 20 or 50 or so. So it is going to, the same thing has been actually realized as a smaller size, and therefore it is going to have the lesser number of computations. So this is the diagram of one such setting. Very interesting to know that if this is the input, so it is going to apply one class one class one convolution, then three class three convolution, one class one convolution, then five class five convolution, three class three max pooling, then one class one convolution, and then concatenation. So these are the values. Okay. The first thing, second thing, third thing, fourth thing, fifth thing, sixth thing, seventh thing, and then there is a concatenation of all these things. So these many operations are done, and then this particular thing, this particular architecture, this particular arrangement is called what? Inception block. So Google Linux uses inception block at these places: 1, 2, 3, 4, 5, 6, 7, 8, 9 places, and it gives them a name as a 3A, 3B, 4A, 4B, 4C, 4D, 4E, 5A, 5B, and they are explained into this particular way, where this is the input size when the what is the input size at that particular time, and they, because I told you now, 1, 2, 3, 4, 5, 6, 7 things are there. This is the first, the second, third, fourth, fifth, sixth. Okay, I think this need not to be defined for 5, 6. This is the only need, because 3 class C is fixed over here. So these six things are defined into this particular way. If you want to understand that what is being deployed at this particular place, you see this particular line. Input was 92 cross 28 cross 28, then 64 1 cross 1 convolution, 96 1 cross 1 convolution, then 128 3 cross 3 convolution, then 16 1 class 1 convolution, then 32 5 class 5 convolution, then 3 class 3 max pooling. On that 32 1 class 1 convolutions are applied, then this filter convolution, then those features are concatenated. You may be asking, sir, how come these values came? So very difficult to tell that how they come up, that what should be the right value over here. Actually, maybe they have tried with the different values, and whatever works best, they have applied over here. Make sense? So very important thing is this, that they have also used the concept of dropout. Okay. Very important thing that is also related to this particular network is this, that the 12 times less connections as compared to the LXNet. It has a less connection. However, 2 times more computation is needed to compute these things over here. Error is reduced drastically from 60%, 16% to 6.4% if you compare with the LXNet. So huge reduction to into the number of things. Also, you can see that here you can see that a strong big change. Earlier you were seeing that the 3 layers were there. Now only 2 fully connected layers are there. So this actually reduces the requirement of number of parameter over here, and actually those parameters can be used over here to build the better features. Next architecture is the very interesting architecture. What it says this, Try to understand what I'm going to say. Let's assume that for some problem, this is the best network that you have. For some problem, this is the best network you have. If I add few more layers, what would be the performance of this new network? Will it be better or worse? You can think that it would be better, because if it is, and if I was telling that that was the best network, then performance would not degrade. Why? Because this network, and whatever is being fed to here, it can transfer over here. Whatever being fed over here, it can transfer over here. It is possible. So, okay, identity mapping, it can do the identity mapping and get the same thing over here. So if I do the things into this particular way, this network is going to be the same. So this is the idea, that if you think that 20 networks are enough, you apply 40 networks or 50 networks, more than this. And if the learning process is correct, then it would give you the right parameter for this thing. With this kind of idea, they had applied on the database. So 20 layer architecture was having the error of this, but they increase the number of layer, the error becomes this. Increase the number of error becomes this. So you can see that this is a bad thing, because they were thinking that if I'm going to increase the number of layers, it should be better, but it is not getting better, it is getting worse. You can see that the error is higher with a more number of error. So the idea was this, but the idea failed because their experiment does not show that this is going to happen. Okay. Why it is happening? It is happening because you know that multiple functions are possible. When you are going to transfer something from here to here, multiple functions are possible. So you can think that let's assume that they can take the value between 0 and 1. How many values are there between 0 and 1? There are an infinite value. What value they should have? It should have 1. So 1, what is the probability that you would get the 1 value? It is 1 upon infinite, because infinite possibilities are there. So ultimately finding out, you know that if you have the value 1, then you would be best. But finding out this 1 is the probability of finding out this value is actually 0. So the main important idea of this particular network, that ResNet, was this, that apart from this idea, they have introduced a skip connection. They told that this network is not going to work. We have seen that this network is not going to work. So I am going to add a skip connection from here to here. So what would happen, that earlier I was if X was fed, I was getting some representation of this over here. But by having this skip connection, I have fx plus what is being transformed over here, plus x is also there. So now instead of single value that I was hunting for, there is two values for which I am going to be interested. Then what would happen, that if I can reduce this value somewhere and I can increase some value here, then I can shift, I can slide towards the right value. By introducing this kind of skip connection, the advantage was this, that they can now they can apply the feature learning process over there, and this feature learning process becomes smooth, because both the values are now can be adjusted, and therefore it was easy to find out, it was easy to slide towards the right value. Earlier I need 1, 0.9 is not working, any other value is not working, only 1 was working. But if you write the equation like this, then nearby values also getting better, and therefore you can find out what the gradient into this particular way, and you can slide and find out the appropriate value. So very large architecture, having more than 150 layers, 152 layers actually, and having the skip connection over there, it was able to perform better than any other method that was available over there. This paper appeared in it was actually a winner of ILSVRC, as we talked about, in 2015. And when it was compared with the second best item that was there, second best algorithm that was there, so ImageNet detection, in the detection, it was a 16% better. ImageNet localization, where the item is, it was 27% better on the COCO dataset. On the segmentation, okay, into the detection, on the ImageNet, it was what I wanted to tell you. So on the detection, 16% better on the ImageNet, 27% on the localization on the COCO database, 11% on the COCO segmentation. So it was way better than the second algorithm that was there. However, the network becomes very deep and it is very difficult to train at that particular time. So, however, there are few more things that are needed because such a big network cannot be trained in a very naive manner. So, this training takes huge time. They applied batch normalization, Xavier special kind of initialization called the Xavier initialization, stochastic gradient descent with the momentum they have utilized. His learning rate was small, mini batch size was 256, weight decay, and no dropout. Using these kind of parametric setting, they were able to achieve this kind of result. So that's all for today. Hope by this lecture you understood that what is CNN and what are the popular CNN architecture and what are their importance and why they are there into the picture. Thank you very much. Thank you for joining.